let's talk about the end behavior of rational functions. End behavior is an equation. It's going to be an equation that we use that tells the ends where to go. Tells the ends of a graph where to go. Okay, there's a couple ways that the ends of a graph can go. Okay, first of all, we talked about horizontal end behavior before, and this would be a horizontal line that tells the ends to follow him. Okay, remember, you can't have a function cross in the middle because he's just dictating the ends. If the degree of a numerator is equal to the degree of a denominator, then the end behavior is y equals, do you remember? A over b. But if the degree of the denominator is greater than the degree of the numerator, then the asymptote is always very easily y equals 0. Remember what we call that if the denominator is greater? Unofficially, of course, bottom heavy. If you notice that the power in the bottom is greater, y equals 0. Now today we're going to talk about some more fancy asymptotes, the first one being oblique. And oblique is a very fancy way of saying on a slanty line. So if the ends are going like this, then they're going to be following an equation something like y equals mx plus b. Okay, oblique is only for diagonal lines. Other is going to be pretty much anything else. Other could be maybe they follow the equation of a parabola. Or maybe the ends go like a cubic, or maybe the ends go like a quartic. Okay, I'm going to draw a graph of ends going like a parabola. Okay, the ends of a graph would be going like that. The middle might have some vertical asymptotes, might have some x-intercepts, all sorts of good stuff. But what you do is you only look at the ends and you say, they go like a parabola. Now, how do we figure out when this happens? If the degree of the numerator is greater than the degree of the denominator. And a quick little way that I remember this is by saying top heavy. So if the power on top is larger, then we do, here comes the good stuff, we do long division. Oh, that's right. That's going to be so exciting. I don't hear any moaning, do I? We ignore the remainder. Okay, so that's good news. You're going to completely ignore the remainder. And long division can be done on the original or the simplified equation. So if you can simplify, factor, get it smaller, it doesn't matter which equation you use to get the long division, and we just take the quotient, we ignore the remainder. Okay, now you don't have to do long division all the time. That's only when it's top heavy. But these are the ways that the ends of a graph can go. So we're going to practice that a little bit today. Our first example right here, let's just go ahead and notice the powers. The degrees are 4 and 3. Okay, and when it is top heavy, guess what we have to do? Some long division. Let's just remind everybody how to do some long division. Which one goes in the divide box? That's right, the one up here. This one goes in the box. Okay, and don't forget with oxes. So in the box, we're going to start off with 3x to the 4th. Now, how about the cubics? I don't see any cubics, so I'm going to say plus 0x cubed. After the cubics come the quadratics, so minus x squared. After x squared comes 0x plus 0. So I'm going to fill in all those terms. We've got all our options inside the divide box. Outside the divide box, your divisor, you don't have to worry about oxes. You're just going to write the divisor right there without any oxes. Okay, now how does long division work? You look at the first one and you compare it to the first one and you ask yourself, what is this guy out here missing that this big one has? He's missing a 3 and an x. Okay, so you just compare your first two. After you get that, you're going to go ahead and multiply it to all three of those terms there. So that gives us 3x to the fourth minus 3x cubed. Oh, I'm really happy I had that column of x's there so my cubics knew where to go. Plus 3x, oh, let's make sure we get him in the right column way down here, plus 3x. And now it's time for change, change, change. You got to change all these signs because long division, this right here is like subtraction. So you're going to change them all to the opposite. Okay, the first column better cancel out. It always does, otherwise something went wrong. This next column here is 3x cubed. I'm going to bring down that guy. Nothing got added to him. Oh, thank heavens there was a column here for negative 3x. And I guess I'll bring down that 0 just in case I need him. Okay, it is time to compare once again. Let's look at this guy, compare and see what is he missing that this one has. This one is missing a 3. So I'll say positive 3. And now I have to distribute that 3 to all three terms. So the first term is 3x cubed minus 3x squared. Let's put plus 3 in the correct line over there. And now it's time for change, change, change. Change all the signs to the opposite. All right, let's go ahead. Our first column here cancels out as it should. The second one is 2x squared. We'll bring down minus 3x minus 3. Let's go ahead and compare the first with the first. What is he missing? Oh, wait a minute. This one's larger. Okay, so right here you keep comparing the first. And when the divisor is larger, then we stop. That is when you stop, when the divisor is larger. So right here, what do we call this leftover thing? That is the remainder. Okay, and what do we do with the remainder? We totally ignore it. So we are ready to say our answer. Okay, the end behavior, the ends of this graph, are they going to go horizontally? Are they going to go like an oblique line? Are they going to follow a parabola? You look at your quotient. Y equals 3x plus 3. Oh, I guess they're going to follow this oblique line. They're going to go on a diagonal line. So we would say that this graph has some oblique end behavior. Okay, we got a couple more examples here that we're going to do, practicing our asymptotes and our end behavior. The first thing that I recommend doing is getting this guy in factored form. I don't think we can factor that numerator at all, so we'll just leave him alone. 2x to the fifth minus x cubed plus 2. And the denominator does factor. That's a difference of cubes. I hope you remember that formula, a difference of cubes. There's a little guy and a big guy. Now, the little guy looks just like him, x minus 3, or x minus 1, and then you have to sop it up. So we're going to have x squared. Then you take one of each of them. 1 times x is just x. Then you take 2 of those. 1 times 1 is 1. And this is the same as the problem. This is the opposite. And that one's always a sum. This right here can never be factored further. So if you're looking for domain, the only domain restriction that this graph has is x cannot equal 1. Are there going to be any holes? I don't think so, because no factors canceled. Does he have a vertical asymptote? Absolutely. He has one right there at x equals 1. Now, in terms of end behavior, let's write a very important note. The ends of a graph can only do one of these things. So I'm going to put a note here that says can have only one. Can have only one. You can't have your ends go like a horizontal and an oblique and a parabola all at the same time. And to find them, we look at the powers. So let's go look at the degrees in the numerator and the denominator. The numerator is 5 and the denominator is 3. So when it's top heavy, what do? That's right, some long division. In the divide box, let's go ahead and put our polynomial with the x's. So 2x to the fifth but I believe there are 0 x to the fourths. Are there any cubics? Negative 1x cubed. How about x squared? There's none of them. There's no x's. Oh, but there is a plus 2. Okay, you do not have to worry about x's out here on the divisor. You just write the polynomial the way he is, and it's time to start comparing. So I look at the first 2, and I say, what is he missing? He's missing a 2 and an x squared. 2x squared has to get multiplied by both those things. So 2x to the fifth minus 2x squared. Oops, I noticed my x squared didn't get a squared. And it's time for change. Opposite, opposite. First ones cancel, as they always should. Otherwise, something went wrong. Let's bring down 0x to the fourth. But wait a minute, we didn't need them. So if you don't use them in the first line, you can just go ahead and cross those off too. I keep them there in case I need them, but if you don't need them, then you don't want to start with them. We'll start here with negative x cubed plus 2x squared. Let's bring down these x's just in case I might need them later. Okay, time to compare the first 2. X cubed and negative x cubed. There's only one little thing he's missing, and that's minus 1. So I'm going to go ahead and say negative x cubed plus 1 way down there. It's time for change. You can go ahead and cancel them, and I'm bringing down 2x squared. Now 2x squared is smaller, so that means this is the remainder. Even though I haven't finished it, I know I'm just going to ignore it anyway. And the end behavior is 2x squared minus 1. Now where are we going to put that? I know it was not horizontal. Did the answer end up being a line, linear, or something else? Since it's something else, you put it in the other category. So if it does not come out to be a linear line, then you put it in the other, if it's cubic or parabola or whatever. Okay, let's practice some more. To get these right, we have to be really good at factoring. So let's go ahead and factor g of x here. Since it's x squared on top, I know it's going to be x and x. What two things make a 10, guys? 5 and 2. Which one should be positive to make a 3? The 5 plus 5 minus 2. All right, the denominator has x times x. How do you make a 15? Do you think it's going to be plus 5 plus 3? You're right. Oh, look what's happening. Now, maybe before I go crossing it off, I'm going to come over here and state the domain while I have all my denominators that I can see. All reals except x cannot be a negative 5 or a negative 3. There's a couple of reasons why it can't be those things. Let's go ahead and cross them off. And as soon as you cross them off, I'm going to ask you, what does that make? And that makes a whole. So negative 5 is going to be a whole. We have to figure out his y value. How do you find a y value? Yes, you use the new equation. So you put negative 5 in there, and you get the fraction positive 7/2. Okay. Anybody left in the denominator? Any vertical asymptotes? Any numbers here we didn't use yet? So the vertical asymptote is going to be at x equals negative 3. Okay, and behavior is the last thing. I'm going to look at my equation. You can either look at the original or the smallest one down here, and the powers are 1 and 1. When the degrees are equal, that means you're going to use the leading coefficients of 1 and 1. So where does it go? It goes in horizontal. Y equals 1. Nothing here, nothing here. Make sure you dash those out. You don't want to leave something blank, because that means you didn't know the answer. Okay, let's do a couple more problems. This one is kind of interesting because it's kind of all separated. So I think what would be a really good idea is to put this over 1 and maybe make some common denominators. So this first term here, he needs to get multiplied by x on the bottom, which due to the bottom, you got to do the top. So g of x equals 2x cubed plus 9 all over x. Okay, that looks a little easier to work with. Domain is all reals except you cannot be That's right. Can't be 0. Any holes? Nope, I don't think so. No holes in the graph. That means 0 must be the vertical asymptote. Okay, there's one kind of end behavior, so let's go study the powers. When the power in the numerator is greater, what do we do? Long division. So let's go ahead and put 2x cubed in the box. Let's not forget about some x's. I'm going to put 0x squared plus 0x, and then we have a 9. And we're going to divide this by just little old x. Okay, what is he missing first? He's missing 2x squared. Multiply that out, that's 2x cubed. We'll change that to the opposite. That's nothing, that's nothing, that's nothing. Oh, I guess we have a remainder of 9. So, I know that it was not horizontal. Did the answer come out to be oblique or something else? Definitely something else. It's a parabola. Y equals 2x squared. So if you look at the ends of the sky, that must be going up, up like that, like a parabola. But there's also a vertical asymptote right in the middle. It's going to go like that. There's a split in the graph. Tomorrow, we're going to take all our knowledge and start graphing these guys. So let's get really good at finding the information so tomorrow you have an easier job. Oh, I like how this one's already factored. It's already in factored form. I'm going to write the domain right away. So all real numbers except, let's see, we're not going to be allowed to use a -4 or a -9. Okay, let's go ahead and cancel those guys out. So g of x can get a little bit smaller. X squared plus 5x minus 1 is simply over x plus 9. Okay, when you cancel out a factor, what does that make? That's going to make a hole in the graph at -4. I'm going to go ahead and let you plug -4 here and have some fun all by yourself. Are you getting a negative answer? Are you getting a -1 answer? Good job. Okay, that means the thing that's left, -9, must be the vertical asymptote. X equals -9. In terms of end behavior, let's go look at this. The original one was a third power over a second power. He was heavy. This right here is also top heavy. So the question is, do you want to put this together and use the old one to do long division or division with the new simplified one? And we recommend the new smaller one. It's going to come out the same way in either case, so let's just be nice to ourselves. X squared plus 5x minus 1 is getting divided by x plus 9. Let's compare the first two. What is he missing? Just an x. And we'll multiply x squared plus 9x. Let's not forget to change. Okay, and don't quit too soon. Some people say, oh, I think we're all done. But hang on a second. -4x, bring down -1, you can still go further. X is missing a -4. But I believe that's going to be the last time we can do anything. If you're positive that's the last step, then you can go ahead and stop. If not, maybe we should keep going. This is going to be -36, but it's going to change to the opposite. That's going to cancel. Yeah, we're definitely done. So how did the end behavior end up? Since we did long division, it's going to be one of these two. It's going to be oblique. Y equals x minus 4. Okay, our last example here definitely can get some factoring. So let's factor the numerator into, let's see, x and x. How do you make a 6? That can make a 5. I think it's got to be +2 +3. And there's also an x plus 3 down here. So g of x actually got really small. G of x is just a line. He looks like a line. So the domain, all reals. Wait, is it all reals? No, we got to say you can't equal -3 from the original problem. But when it canceled out, that makes a hole at -3, comma, go figure it out. Yep, put into the new equation. That comes out to be -1. So he does not have any vertical asymptotes. In terms of end behavior, this is where it gets a little tricky. If we do long division with this, and we take x squared plus 5x plus 6, and we divide by x plus 3, I know the answer is going to be x plus 2, and everything's going to cancel out. So you're telling me when factors cancel and you get a line, your end behavior follows a line? Well, of course the graph follows a line. The graph is a line. So he does have end behavior, and the end behavior is going to be oblique, and you call it y equals x plus 2. If you want to go ahead and do the long division with the original, you're going to get that answer, or you can just remember when everything cancels out and makes just a line, then your ends are going to follow a line. All right, I hope you guys can determine if it has different types of end behavior and know how to do long division to find them. Best of luck. See you tomorrow.